Okay, everyone, welcome to today's seminar. As you may notice, I'm back, so it's going to be great. And today it is my great pleasure to introduce our speaker, Boris Daszuta from the University of Jena, Germany. And Boris is a PhD at the University of Otago, and he's going to be talking to us about something which I find very interesting.
Right, so let's get started. Thank you very much for being invited to do this thing. But you made a terrible mistake. You have already given me the shirt, and so now I should just run away and claim that everything is done.
Next time I will not make the same mistake.
Okay, so yeah, I guess the general idea today is that I wanted to talk a little bit about GR-Athena and efforts that we've been making in Jena together with collaborators, as some of them are listed on this slide. Roughly speaking, I wanted to have this in two pieces. So there will be sort of, if you're unfamiliar with this kind of code/approach, then I'll give some general discussion of this. And then in the second portion, I wanted to talk a little bit about compact finite differencing and application of that method to numerical relativity. And so, okay, well, you know, there are a lot of codes. Why should you want to write another code? Or what is the kind of initial motivation for doing this? And so our initial intent was to look at, also I will say, please feel free to attack. It's a nice small room. Just as a question, go for it.
Also feel free to stand if you're not comfortable.
Oh, no, I mean, I'm like this kind of person that's always, but okay. Yeah, so our initial motivations were thinking about intermediate mass ratio or extreme mass ratio. And, you know, it's a funny situation that we're all in, because there are a variety of, let's say, mature NR formulations that can be deployed on exploration of phenomenology in this kind of problem area. However, in order to kind of probe it, you really do need to deploy code on performance machines. And the snag here, let's say, is that many NR codes are not so efficient at scale, which this is a bit of fun. So the idea that we had was to shift things to a kind of oct-tree grid structure. And you'll see why this may be a good idea shortly. So, okay, we built GR-Athena, but we did not start from scratch. We started out with a nice framework, Athena++. So what is that? Well, that is this astrophysical MHD code. And this is nice in the sense that you have the ability to solve MHD problems on prescribed backgrounds. So here I have in mind, you can specify, let's say, a stationary space-time line element, and then you can solve some problem on this. Another nice thing about this is that, well, you have this kind of modern modular C++ approach, which, okay, depending on tastes of programming, you may like or may not like. But the point is that it's nicely modular and things are split, and there's a nice sort of hierarchy of logic and how to split things out. Just to fix some nomenclature, because it would be helpful in a bit. When we're thinking about a computational domain also, we're thinking about an overall omega, and we can consider this at a first step as being represented by a logical in rectangle. And then related to this, you have various meta considerations, such as quantization, details of boundary conditions, spatial extent, etc., etc. The thing, I guess, to remember really from the slide is that if I have an n sub m, then I'm talking about a number of samples that are living on the mesh, or it's an n tuple with a number of samples in each direction. The way that this code splits the domain is an initial decomposition. So you have your mesh, and then you split it into mesh blocks. And the sampling of the mesh blocks needs to divide the mesh samples. And so, okay, at the end of the day, you are in this situation where you have a family of n rectangles that are describing your computational domain. Fine. So what is this oct-tree business? How does that relate to things? Well, here I have some sort of figure which is meant to represent this. So you can imagine this as, roughly speaking, being a initial decomposition. You then think of the geometric centroids of the elements of this decomposition and trace some line through their center, which is described in a particular Z ordering. The point here is that if you imagine this as a one parameter thing, then a suitably small perturbation in that parameter will leave you suitably close in the ambient space, so in 3D space. And so what is the advantage of this? Well, if you look at this sort of thing here and you split it into two pieces, and you imagine that stuff to the left is on one MPI rank and stuff to the right is on another MPI rank, then you gain an advantage in the sense that, okay, on this MPI rank, data that I need from nearest neighbors is in memory, similarly over here, and this becomes quite efficient. So you get this kind of data locality. And this translates to the refined context also. There,
so before, how would you choose? Because the ordering, like here, is not like 0, 1, 2, 3, and then it goes down and then goes up. How would you choose that?
So this is encoded through this so-called Morton order. So one can use other types of ordering. So if you're really hardcore into that sort of stuff, then one could, for example, think about the Hilbert curve, space filling thing. It may be slightly more efficient, but doing that may be a slightly larger headache, let's say. So this was already there, so we used it. Okay. Similarly, for mesh refinement, the usual restriction is that you have this kind of 2-to-1 ratio where you have a block and then a nearest neighbor is on the same level, or 1 times refined / derefined, let's say. Okay, so that's what Athena++ is. Now, well, what did we do? Well, we took this kind of as a base, and then we introduced a whole bunch of additional things that are required for NR. So in particular, we wanted to have high-order finite differencing. So we do this kind of, C++ thing, you template the stuff, and then you have it. To make life a bit easier, we also introduced some additional infrastructure to deal with tensorial symmetries and so on. It's a little bit funny being here and telling people about Z4C, but you guys know all about this. So just to maybe say it in a sentence, we have a nice, strong hyperbolic formulation, and we describe our binary black holes, let's say, in terms of punctures. So kind of a standard thing. The nice thing about this is that the location of these punctures are also nice for serving as an AMR criterion. So you can preferentially refine to the location of these. Okay, another thing that you need is, well, you want to be able to extract various, let's say, diagnostic quantities or scalars such as energetics or gravitational wave information. And for that, it is, well, good to have spheres. So what we did is we introduced a module to deal with geodesic spheres. And then another thing that we did is we extended the treatment to also be incorporating a vertex-centered sampling. And I will say now why we did this. This slide I will skip over because everyone here knows all about this. Maybe just for concreteness, let's say, when you are evolving your whatever formulation, it's always quite particular what you are doing at the boundaries. And just to highlight, we are doing a sort of very straightforward Sommerfeld thing. Okay, but coming back to the variable sampling strategy. So you have a code that allows you to do self-centered, face-centered, when you're dealing with various hydro quantities or you're dealing with fluxes and so on. Why would you want to do another sampling? Why would you want to go to Pacific? Because this requires a lot of infrastructure change and so on. So a nice way to understand this is to think maybe in 1D. And so here I have this kind of sketch here where you have a grid and then a finer grid. And you will observe that if you're in the vertex-centered situation, then interspersed nodes coincide. And so one nice thing about this is that if you're thinking about transferring data from fine to coarse and vice versa, and you are imagining accomplishing this with a polynomial interpolation method, then on these coincident nodes, you will have your operation reducing to an injection. So it becomes quite efficient computationally speaking. On the other hand, well, there are always disadvantages. So a disadvantage that you can potentially immediately see is that, okay, I've got this block here, and that's nice, and it will have a neighbor. And these blue nodes will be shared between these blocks. And so you need to deal with this information consistently. And so, of course, we're solving hyperbolic PD, so this can be a little bit of a sensitive issue. Actually, that becomes more of a nightmare when you think about it in 2D. So you've got this, let's say, local view of a mesh, where I've got a coarse block here, and then to the right, I've got 2 finer blocks. So I suppress the one that should be down here, but okay. And you can see that, oh, some of these nodes which are shared between these blocks will either be shared between only one other block or perhaps 2 other blocks. And so there's a kind of multiplicity consideration that you need to take into account in order to deal with this. And so we do this dynamically. So essentially, if you're thinking about it in the communication sense, then you have a buffer of data that you want to pass in order to populate ghosts, and then you want to unpack this buffer into your local memory where you have your fields discretized. And so if you add these things together and then divide through by the number of nodes that things are shared by, everything works out, fortunately. Okay, so the next thing to make mention is the geodesic spheres. So here I say this only very kind of coarsely speaking. We construct these in order to essentially exploit for numerical quadrature purposes. So when we're wanting to do GW extraction, we build the Wild scalar, and then on these spheres, we can project onto spin-weighted spherical harmonics and get information on side 4 out this way. Okay, so you're in a situation where you do all of this stuff, and it's a bit involved, let's say, and you want to be able to test it. And how do we go about this? Well, at first step, we have this mesh, which is quite particular and a bit distinct from something that you would experience in, let's say, Einstein Toolkit or BAM, where you have this overlapping box structure. But what we can do is we can say, okay, we'd like to emulate a resolution hierarchy such that we can compare sort of like with like. So this is what we do. We generate initial data using standard two punctures method due to unsolved, basically. And then we compare. So we compare first against BAM. And we can also do a comparison where we generate a longer waveform, which is pertaining to an eccentricity reduced event, and compare that using effective one-body model. And yeah, in order for things to pass, absolutely everything needs to work simultaneously, basically. So it's quite a demanding thing to do. Maybe just actually give you a better sort of sense for what the grids look like. We do a 2D slice, and we imagine at first instance our two punctures sitting here, then on axis. And then you imagine a short duration of evolution where you've got a co-orbit going on, then the grid adapts to this. And again, the thing that I want to emphasize here, these blocks really are not overlapping apart from the ghost zones. So it's not this kind of flattened thing where you have a box that you need to communicate to another box, which is sharing data. It's just the interface and then ghost stuff that needs to be communicated. Okay, so that's the kind of a mental picture to have. The concrete test that we did initially was this so-called calibration test. So this is a short duration DBH in spiral, about 2.5 orbits or so. And then, okay, there's a litany of details. Essentially, you pick the number of ghosts that you want. That fixes the finite difference in order. And then you have a particular choice of the time evolution. And so as standard, we pick the for the RK method. And then, okay, the question is, what quantity do you want to inspect to verify that things are working properly? Well, the particular quantity we inspect is psi 4, or relatedly, the gravitational strain. In a newer development, we can also do Cauchy characteristic extraction, but this requires some external processing, let's say. So you extract stuff onto spheres, and then that is evolved with an external code. So, okay, well, let's look at the trackers and look at the waveforms. Well, we get trackers from BAM, and we compare them to the trackers we have, and we find things falling on top of each other. Great. Looking more carefully at waveforms, we look at the 2-2 mode of the strain, and we find that to a very good agreement with BAM, things are looking nice. So in particular, the phasing is very close. The amplitude differs only very slightly. And so, okay, that's fine, but to be careful, you want to do a convergence test. So we do convergence test too. In the left panel, this is for a fourth order spatial discretization. In the right panel, this is at 6th order. And the point here is that, okay, you can do a run at a fixed resolution, then you bump the resolution up. And if you have a consistent implementation and everything is working as expected, you know that the error should decrease at a given rate. So you've got a convergence factor that you can compute a priori. And then if you look at distinct resolution pairs, you can rescale them by this convergence factor. And in principle, if you're in the convergent regime and things are playing nicely, all these curves should fall on top of each other. And so in the left panel, you see this. In the right panel, it's a bit noisier, but here if you actually look at the data that is computed, you see that it's basically probably at saturation in the sense of convergence. So this is the 2-2 mode, so the phase of the 2-2 mode over the full sort of duration of the event. But another thing you could do is you could say, oh, okay, I'm going to fix time at merger and then inspect convergence at that time. And so this is what is done here. Again, a similar sort of conclusion can be drawn that, okay, in the fourth order case, well, let me rephrase. Let me say that what we do for this at merger comparison is we pick a very high resolution and then increase the resolution of runs and compare against that as a reference point. But it's basically the same sort of game. So here we find something that is consistent with a fourth order convergence for a fourth order method. In the case of the sixth order method, it's a little bit noisier, but again, jumping back, you can see why. You would not anticipate that it would be extremely clean. Okay, so calibration run, it's a short duration event. So this is nice because you can quickly iterate when you're developing and testing stuff. But the point is that we want to look at, eccentricity reduced gravitational waveforms, lots and lots of orbits. How do things perform in this situation? Well, such things are more expensive computationally. So we can ask two questions at once. We can ask, how well is it going in that physics problem? And then can we actually reduce some of the cost? Because we do have a fair amount of freedom in the sense of how we are refining our mesh. And so this is kind of the point here where I fix a mesh level resolution, and then I want to have roughly the same number of mesh blocks as I add more and more levels of refinement. So this NL, yeah. And this should be NB, but okay. What is probably important to pay attention to in this table is that you have two sequences where xn is meant to fix the extent of the spatial grid, and when one is doing a comparison for convergence inspection, one should always pick the same domain or spatial extent. Otherwise, you are introducing systematic. So, okay, we do this. And very similarly to what I was showing previously, we do this kind of, okay, this is the anticipated order of the scheme, and this is the convergence factor, and we can rescale things and check that, okay, indeed, everything is performing as expected. And well, we do that and we find that it appears so. So in the upper panel, I'm looking at the phasing in the 2-2 mode. And then in the lower panel, I'm doing this slicing at merger time. And so things appear consistent with the sixth order trend, which is good. You can also do something else. So instead of just doing this kind of consistent convergence testing, you can say, oh, well, I know that there are nice models based on effective one-body theory, and they are also informed by NR. So in principle, I can look at what my waveform output is and compare against that. And so this is what we did with TOB resums for this same simulation that I was showing. And you can find that, okay, you have good phasing properties to merger and then to the ring down. The thing maybe to point out for me here is that, okay, when we're computing gravitational waves and we're extracting them, for this plot in particular, because we have done the convergence analysis and we have identified the order and said that, okay, everything is consistent, we can do an extrapolation. So the Richardson style argument where, okay, if you know the order, then you can extrapolate out. Okay, so fine, things are looking to be behaving consistently and so on. Well, we should probably check the performance in the sense of execution. Like, we did all this work, it appears fine, but is it still performing? Okay, and to this end, we do two things. So we do a so-called strong and weak scaling test. So in the case of strong scaling, you are, as you see, picking some problem size and then throwing more and more sort of machine power at it, if you like. In the sense of for weak scaling, what you are doing is you are scaling the problem size with the amount of machine power you're throwing. So, and then just to mention, this was done on machine Supermuk NG at LSF. So this is some cluster in Germany. So first we examine the strong scaling, and here you have different series where you have which are separated by resolution. And so everything is with respect to the first point, if you like. So on the left side, you've got efficiency and then speed up. And then you see that it's being swept with number of CPUs. On the right, one has to be a little bit careful because we have developed this thing which is based on a task-based paradigm. So you've got Athena++. The idea is that you put a piece of the calculation that is to be executed and you sweep through this list of tasks. And then when it's appropriate, a task is executed. So maybe more concretely, let's say, you need, when you're doing this time evolution to calculate the right-hand side of the system, you need to communicate data and this kind of stuff. And so if you have a classless thing, then the right-hand side gets evaluated on one machine, but on this other machine, something else may be more appropriate to deal with. And so what this plot is investigating is how much work do I need to provide to various CPUs in order to saturate them such that I am actually in an efficient regime. And so here you see that, okay, there's some sort of cut where maybe on the order of 10 mesh blocks per CPU. If you're working at fourth order finite differencing, you need to have this much in order for things to be efficient. Similarly, for the weak scaling, well, recall again that you are scaling the problem size up with the number of resources. And so in principle, what you would really hope to observe is that the amount of CPU time per MPI task is basically constant as you do the scaling. So you want a flat line. The nice thing is we find this flat line. As a further sanity check, what one should also do is ensure that, okay, I'm running a code and presumably most of the time should be spent in actually computation, i.e. right-hand side evaluations and so on. And so this is what the lower part of this plot is showing you, that, okay, if we bucket things that involve right-hand side calculations, then certainly this is where the predominant amount of time is spent. And of course, if you're thinking about CPU time per MPI task, then smaller is better. The two distinct series of data being shown here are compiling with new versus Intel. That's a finer point, and we can discuss that later, but okay. So now to maybe change tack a little bit, I've told you a little bit about GR-Athena and showing you that, okay, we have this performant code, things are consistent, so we can use that for various production runs and so on. What about this compact finite differencing business? Why would you want to think about this? So recall that when we're doing in our simulations, we are really interested in, let's say, computing gravitational waves, and in particular, we want these to be long duration, and we want very high accuracy. I mean, when you're thinking about detection efforts, then you're feeding a template bank, which is based on, let's say, some EOB output, which is informed by this stuff. So that's the motivation. But we can make a couple of observations. Observe that if you think about hyperbolic PDA, so think about the simplest prototype, just an advection problem, linear thing, the phasing of this is very well captured by spectral methods. So these are global methods, and you're working with smooth approximating function spaces. On the other hand, make another observation that when you're involving, let's say, hydro, then you're going to be potentially encountering things where you have reduced smoothness. So you need to be able to deal with shocks and so on. And so you have this kind of two opposite ends of the global methods versus local methods. And well, the compact finite differencing is kind of towards the, it's a local method certainly, but it's living more towards that end, but it's trying to blend some of the advantages where you get improved phasing from this other side. To give you a bit of a picture as to what I'm talking about, if you are not familiar with these, I have a diagram here, and what would I like to do? I would like to compute the value of the derivative of some function based on data that I know. So if I'm talking about explicit finite differencing, then let's say I know function data fd0 at these black points. And in the explicit case, let's say I want to compute it at this crossed base point. Well, you do that, you take a linear combination of these points that you know, and then out comes your approximate curve. In the compact finite differencing case, what you're doing is you're saying that, okay, I've got this data, I want to compute this unknown, but what I'm going to allow for is to couple another unknown, so a nearest neighbor or next nearest neighbors and so on. It turns out that this helps a lot with phasing properties. to say this another way, well, you are forming a linear combination of stuff that you know, and then you're relating that to stuff that you don't know. And here, what I'm saying is that, okay, I would like a method to construct a stencil or a scheme or an approximate. And so I have this ansatz, which I make, and then I want to specify some coefficients alpha and beta, and they will fix the derivative approximate scheme. One way to do that, well, you just Taylor expand your function and do matching, and then you get some linear constraints out. Fine. But you can be a little bit sneaky, and you can say instead, well, I'm actually not going to match to absolute every single order that I can. I'm going to leave some underdeterminedness in this problem. So again, I want to figure out what alpha beta are. I can put some linear constraints on this problem, but I don't want to fully fix this. The idea being that, well, I can cook up some characterization of spectral error, and then maybe have some nonlinear functional that I can optimize against and reduce that. So this is exactly what I'm saying here. And sorry about some of the details, but the main point is that, okay, I make this ansatz, and then I say, okay, let's differentiate plane waves. Trivial problem, write it down, and then you write down the, or what would be the discrete approximate to this problem in this G hat thing. Why would you do this? Well, this is nice because you can immediately cook up a nice characterization of spectral error. So in particular, I have this normalized and modified wave number. And you can consider the difference between these and then throw them under a weighted integral. And then you say, oh, okay, I want to reduce this epsilon subject to some choice of weight. The choice of weight is quite flexible. You can pick whatever you want, but for simplicity, we just pick a cut. Okay. How does that look? So let's jump back to something that should be familiar. I do explicit finite differencing. I'm doing it at sixth order. So in this left panel, I compute a first derivative, and then I can look at what the modified wave number is. So if you do this analytically, well, it's a plane wave, so you get just a line, right? So that's this black thing. If you do explicit sixth order finite differencing, you get the blue line. If you do a lopsided stencil, which is important when you're thinking about dealing with the vector terms, then you get this orange thing. But now, if you look at the most basic compact finite difference sort of thing that you can cook up, you are already doing a lot better. So the difference between the actual analytical result and then the modified wave number, you can see in green, for example, here. On the right-hand side,
did you find out what the modified wave number was?
Yes. So for modified wave number, I have this expression in here. So this eta tilde is computed based on the approximate that you're constructing. So you're approximately differentiating a plane wave, and then you're saying that, aha, that is the modified wave number that I can peel off. Does that make sense? Okay. Right. So on the left, first degree derivative. On the right, second degree derivative. That's nice. We can do that in 1D on a periodic domain, let's say, and those schemes, well, they're implicit, so they're coupling neighbors, but you're not actually in that situation. If you're thinking about now, back on the numerical relativity problem, you're in a situation where you've got a domain which is partitioned. And so you need to cook up some way to deal with this partitioning and then to preserve some of the advantages that these methods may confer. So how do you do that? Well, one approach to that end is to say that, okay, on the interior of my mesh block, if you like, I can fix the scheme which I construct through this optimization process I described. On the boundary, I provide some alternate prescription to deal with this. So you can imagine that, okay, if I've got a characterization of dispersion and so on the boundary nodes, I could conceivably come up with some explicit stencil, which is larger than the equivalent order scheme would be usually. But the point is that it matches at lowest order dispersion error. You could go further. So you could imagine that, okay, I jump back and I imagine this situation here where I've got a base point that I want to compute something at, and I've got a neighbor coupled to the right. On the left boundary edge, I don't need data from the nearest neighbor block to the left. So in principle, what I could do is I could imagine on the right, where I do need the nearest neighbor data, to impose the explicit prescription and then iterate once and communicate back this data and close it not with the first explicit thing, but with the update. So you iterate data and you, in principle, improve the solution of this numerical system. And just to see, okay, why you would want to go about it in that way, let's cook up some smooth function and let's just play around with first degree derivatives related to that. So on the left panel, what I'm showing in the uppermost portion is this function g that has been normalized. The function, the first derivative, and the second derivative. In the panel in the middle, what I'm showing is taking one of these compact schemes, which I construct. You can see that, okay, this is some funny notation, but the point is that you're coupling only a neighbor to the left. And if you close it with the explicit description, then you will find that error is maximized towards the left boundaries. So this partitioning here is reflecting the fact that, okay, you've got multiple mesh blocks. And I'm imposing this approximate thing on the left boundary of each mesh block. If you do the iteration, then this decreases the error and it converges or looks like it becomes what you'd get if you just were to deal with this whole situation in a global fashion. On the right panel, I'm showing a variety of different schemes that are just testing this idea. But it appears that in all cases you can do this, and there's nothing special about this function. You can use whatever sort of function it is just for the sake of example. Another way you might like to think about these things is, okay, we like toy problems because, well, we get the first sense of how things go. And a kind of canonical toy problem here would be some advection style thing. And so let's concretize that and say, oh, let's do a 2D advection. Again, just a linear, simple thing. And let's think about the semi-discrete system. Actually, let's look at the eigenstructure of the system. We put in whatever approximate that we're wanting to utilize. So we can use an explicit finite differencing, we can use a compact whatever. You plug it in there and then you compare. What is the global discrete approximate that is representing this linear operator? And then you compare that to the domain decomposed analogous version. And so you pick the resolution such that things match up and so on. And so on the left panel, I show this without, so just using an explicit closure. You see that this E3, which is the standard sixth order finite differencing, well, nothing should change if you're comparing globe versus domain decomposed. So in open circles, this is a global version. With the crosses, this is a domain decomposed version. So because it's explicit, it doesn't need any funny business. These things are coinciding. Similarly for the lopsided, on the other hand, you see that, okay, if you deal with these compact objects, then here you have a spectra that gets deformed. This is bad because, well, you're starting to lose some of this nice phasing advantage that is conferred by these methods. On the right panel, I show the same thing, but just iterating once. So I close with the explicit stencil that's meant to match the dispersion error. And then I do an additional communication and then utilize this updated value in order to re-approximate things. So doing that and looking at the spectra, you can see that this basically cleans everything up. So this is nice. Okay, so, you know, I could now go into showing you convergence plots of this and so on. I mean, you can look at this operator and you can say, you know, I want to go outside, and what I'm going to do is I'm going to evolve this with some exponential method, and it'll be fine. And then I'll just look at the spatial problem or the spatial convergence of this, and you'll find if you do that, that you get what is expected. For this class of problem, just to give you a sense, if I compare sixth order finite differencing with the sort of simplest unoptimized compact finite differencing, I get something like an order of magnitude improvement in phasing if I think about the situation where I'm doing 100 crossing times on a tutorials. Yeah. So that's it. Let's just attack the problem that we actually want to solve. So how are we going to do that? Well, previously, we looked at these binary calibration problems and then this exagescally reduced thing. So let's go back and look again at the BDH calibration problem. And let's deal with the finite differencing by just making some formal replacements. So we'll replace the explicit finite differencing prescription with this compact stuff. At a first step, we will just utilize explicit closures for this problem because it's quite involved if you actually want to code that carefully. You do this, and then what is sort of a simplest first check that you can make? Well, if you're talking about NR, then often people like to go with apple-with-apple tests. And so the point here is that you do a sort of robust stability check, which you put some noise, and then you make sure that this noise doesn't get amplified. So we did that. We found things performed as expected. We didn't get this amplification. You can do a gauge wave test. We did this. And in this domain decomposed setting, even just with the explicit closures, we find a very nice improvement when you're comparing explicit, so just the standard explicit finite differencing versus compact. So you can get order of magnitude improvement. However, what we want to do is we want to look at BDH, but here you need grid refinement. And so we do that. And then there's a question, okay, is it stable in this situation? So it turns out that these methods appear, at least from numerical experiments such as this, to perform stably. On the left panel, I'm showing the side 2-2, or the real part of this. And then the inset is meant to indicate the methods that are being utilized for a given ROM. So in blue, the standard explicit finite differencing, so centered operator E3, and then the lopsided 4-2. In orange, I have sort of the simplest Pade compact finite differencing that replaces the centered operators, but leaving alone the lopsided because they are a little bit delicate. Similarly for the green, it's just a different compact scheme. And then for the last option in red, I replace everything with the analogous optimized compact finite difference. So in each case, things appear to work, which is nice. But then the question is, okay, well, how can you further optimize this in order to improve the quality of waveforms and so on? And so here, I think this is still a little bit of an open question because we are not being particularly careful with what we're doing at mesh block boundaries. So we're not doing this additional communication. And then the thing that you can imagine is that jumping quite a bit back now, we have a situation where we decompose a domain and then we have error accumulating towards boundaries, mesh block boundaries. Now, if you think about the grid refinement hierarchy, so if I jump back now significantly further, if you have error that is being induced at boundaries here, and then on top of that, you're doing level-to-level transfer, it is a potential situation where this may get amplified if you're not careful. So we have not looked extremely carefully at this. It's a thing to do, but it's a thing to keep in mind also. Nonetheless, we can construct convergent series, and we can verify that at least the order is performing in a way that we think that it should, i.e. we have the prescription at fixed, let's say sixth order, we should observe sixth order trends that things are going as we think they are. And indeed we find this. So we have the compatibility with sixth order showing that. Okay, so maybe just a little bit of an outlook. I discussed the GR-Athena and showed you that, okay, we've got this nice functionality, things appear to be working consistently, things remain nicely scalable, and we can use this for production BDH runs. Another kind of little bit interesting thing is that you can actually use compact finite differencing in NR. it remains a situation where you probably want to tune that further, but it's possible. Some parallel efforts that we are also working on, but I just didn't think I should discuss here, is we continue to work on coupling the matter sector. So we have GR-HD well under control, and currently we are working on dealing with the MHD. The same sorts of questions can be asked, like, do you have consistency? Do you have scalability? Yes, and yes. Another novel thing for me to mention is that there's also some work underway to do with Cocos. So there is also an Athena K, which stands for Athena, well, with Cocos enabled. And here the idea is that, well, emergent sort of trend with HPC is that, or high performance computing, is that there is a push, I guess, due to the AI people wanting more and more GPUs, that you have heterogeneous architecture. And what Cocos allows you to do, if you're familiar with C++ coding, is that essentially this is a header-only thing that you can template and you can place in your code, and you can recompile things depending on the target architecture that you want to execute further. And so some work has been done doing kind of an equivalent GR-Athena thing, but with Athena K. And there, the state of things currently is that unigrid runs for a single puncture are stable. We have already made some initial efforts towards the BBH merger problem also. But okay, that's all from me. So if there are questions, I'm happy to start answering.
Thanks very much. Very well timed. Do you have questions? Okay, Hans first.
So for the convergence test, what was the property you were given?
Your phasing. Yep. I mean, okay, you can be a mathematician and say, no, I want that in a particular norm. This is not blah, 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 but everyone does it.
Okay, so the phase of the gravitational wave for some form.
Yeah, so true.
Is there any not really complicated, but people have other configurations that nice full order actually is very substantially less that it might extend or something. I think very shows clear convergence. I'm wondering, so do you think that we need to do better than any other setup? Or if you change the configuration, actually, will you suffer from the same problem?
So now you're asking a robustness question, basically.
Yeah, like do you think so? I mean, have you talked with large things and you see the same like the full order across a large swathe of the parameters?
So you've been prioritizing running some BBH scattering stuff. There it appears that performances as we observe here are persistent, but in the case of large spin, I'm not so sure. I mean, also the initial data set itself is limited in the sense that you can't push it necessarily as far as you want, because it's the two punctures unsolved.
Do you have more questions? Oh yes, I'll start asking. So, yeah, sorry, you have one. Go for it. Go for it.
Said you and asked about convergence and norms and so forth.
This is the proper thing to do.
Yeah, that is really the proper thing to do. So even looking at, I agree that everybody does it. You're looking at something that is okay, it's the deliverable that you want.
Yep.
But from a pure analysis point of view, it's not really what you should do. Right? You should look at
This is hectoring, but yes, we have done this. So for example, you can look at L2 norm or Hamiltonian constraint or things like that.
Yeah, and do you see something like this?
Yes. Here you may have an issue with the puncture region itself. So if you do, but this is I guess the standard thing. So if you do an evolution with the gauge that does not involve that, then everything is clean and it's fine. But if you're looking at punctures in the vicinity of the puncture, you may have a problem. So you may want to, let's say, excise part of it and look at convergence further away. But yeah, you have to play some games to deal with this.
So I was first going to ask how GR-Athena ++ compares to Dendro GR. Like in the different infrastructures and how you, from your knowledge, how they compare, for instance.
So Dendro is a similar sort of oct-tree idea, but the distinction with them is that they're using multi-resolution analysis to generate the grid configuration, I guess. In similarity, they are still using finite differencing. So this is a question that I would have for them. Can they utilize the multi-resolution analysis to do the differentiation process itself? This may be a little bit involved of a question to ask, but it doesn't appear that they do that. Okay. So that is one thing. They show sort of nice scaling properties and so on. I'm not sure that they really have had a huge amount of actual science output in the sense of providing waveforms or energetics or this kind of stuff. I think for them, at least so far, and I'm not trying to bash them or so, it's been just developing this kind of nice shiny code. Thank you.
So another question I had is that so you mentioned like all the development of the vertex-centered like using the finite difference in the vertex for the developed. Then afterwards, when you were talking about the compact finite differences, at least in the picture, it appears. Did I understand correctly? It looked more like
No, you're correct with that. In this picture, this is looking like it's on cell centers. I made this image like this to just avoid having people worry about what's happening there. In principle, the same treatment goes through, so I have it implemented for both situations. The performance is also similar, which is a little bit interesting because in the vertex centering case, you have this kind of averaging procedure, so you think, okay, maybe somehow this smooths out some of this boundary stuff, and you don't have to think about it. But no, you do have to think about it. It's still involved.
And with respect to cell-centered versus vertex-centered, did I understand correctly that the main motivation for the vertex-centered was also performance?
Performance, yeah.
The overlapping, so you can.
Yeah, because the RP becomes very, very cheap, so they restrict for longer.
Okay. Are there any questions? Oh, yes. Yeah, I actually wanted to ask you, when you mentioned that you could do CCE, coalescences extraction, do you assume correctly that the code you'll be using for the propagation from the geodesic spheres, that would be the one developed by the SXS people, or you have a known?
This is a very recent development. What we do with that, I guess I didn't put any details. We take metric quantities and we extract them on spheres, but the way that it's currently done within the code is that it's extracted on a what do you call it, the regular grid, so just the tensor product of the theta field.
Okay.
So it's not on the geodesic spheres. And then the idea is that, well, we can dump that and then evolve it with, say, Fitnal code.
Okay.
In principle, it would be nicer to use something that's a hacked out of Spectre or so, because they are a little bit careful with that. But yeah, for now we did that. It's a similar sort of idea to, we also have some apparent horizon finding technology, but for now it's also working with this kind of cool sampling sphere rather than the geodesic.
Any more questions? So I have some more, but I think they're more technical, so we'll get asked later. So 3, 2, 1. All right. Let's speak again.
If you enjoyed the video, like and subscribe.